In this video, I am going to explain the charging concept of the capacitor. First one, circuit diagram. This one is voltage source V. This one is a switch. Resistor R and capacitor C. The instantaneous voltage across that capacitor is given by Vc. The current flow through the circuit is I. Switch at t is equal to 0, the switch is closed. The switch is S is the switch S is closed. In the last video already I have derived the voltage across the capacitor. Vc of t is a function of source voltage V into 1 minus e power minus t by R into C, where V is called as a source voltage. R into C is equal to tau is called as a time constant of the circuit. T is the time. T is time. R is resistance. C is capacitance. Vc of t is the instantaneous voltage across the capacitor. Instantaneous voltage across the capacitor. These are the parameters which are present in the derived equation. Vc of t is equal to V into 1 minus e power minus t by Rc. Product of R into C is called as a time constant of the above circuit. V is the source voltage, R is resistance, C is capacitance. Vc of t is the instantaneous voltage across the capacitor. That voltage changes with respect to time. Here Vc of t is equal to V into 1 minus e power minus t by Rc. At t is equal to 0, the switch is closed. The instantaneous voltage across the capacitor Vc of t is equal to V into 1 minus e power minus 0. E power minus 0 means 1. V into 1 minus 1, that is equal to V into 0. 0 volts initially. As t value, time constants, t is equal to Rc, t is equal to 2 Rc, t is equal to 3 Rc, and so on up to infinity. The time constant value increases. The instantaneous voltage across the capacitor is also increases, shown in figure. At t is equal to infinity, the instantaneous voltage across the capacitor Vc of t is equal to V into 1 minus e power infinity. Infinity by Rc means infinity. E power infinity means V. 1 minus e power minus infinity means 0. Therefore, at a t is equal to infinity means steady state condition has been reached. The instantaneous voltage across the capacitor is the source voltage. That is, this is the instantaneous voltage. Vc is equal to is the source voltage. That means the capacitor is fully charged at t is equal to infinity. At t is equal to 0, the capacitor acts as a short circuit. Capacitor acts as a short circuit. Acts as short circuit at t is equal to 0. There is no voltage, therefore that is the reason the instantaneous voltage across the capacitor is equal to 0. As time goes on increases related to different types of time constants, the charging instantaneous voltage across the capacitor also increases. This is the graph. According to graph, time versus Vc, instantaneous voltage across the capacitor, Vc of t at t is equal to 0. Vc of t is equal to 0. Different t value is changed from different values of time constants. That means RC, 2RC, 3RC, and so on. RC means tau, 2 tau, 3 tau. At t is equal to time constant of the circuit, product of resistance and capacitor. Vc of t, instantaneous voltage across the capacitor, is equal to V into E1 minus e power minus t by RC. The t is equal to RC is substitute in this equation, e power minus RC by RC. That is equal to V into 1 minus e power minus 1. That value is 0.632 volts, 632 times the source voltage. Here, as time constant goes on increases, this is the V is the steady state value, steady state voltage. As time constant goes on increases, the voltage, instantaneous voltage across the capacitor, Vc of t is also increases like that. At t is equal to infinity, it reaches to V volts, source voltage. That means the capacitor is fully charged. At t is equal to RC, the value is 0.632 times source voltage. Now we will see at the t is equal to infinity. T is equal to infinity, the instantaneous voltage across the capacitor V of C V into 1 minus e power minus infinity by RC. That means minus infinity. That value is 0. That means V. The capacitor is fully charged. This value is V at t is equal to infinity, Vc of t. This is the charging concept of the capacitor. Next one, current, instantaneous current or charging current. Charging current. The derived already derived equation. Consider derived equation. Vc of t, instantaneous voltage across the capacitor, is equal to V into 1 minus e power minus t by RC, where R into C is called as time constant of the circuit. V minus V into e power minus t by RC. Vc of t. Vc of t minus V is equal to minus V into e power minus t by RC. Change in notation. V minus Vc of t is equal to V into e power minus t by RC. This is the considered circuit diagram. V, the switch is the switch S is closed at t is equal to 0. At that instant, suddenly closes means initially there is no instantaneous voltage across the capacitor. The capacitor acts as a short circuit at t is equal to 0. The capacitor acts as a short circuit. Some resistance value is included in this circuit diagram. This is the R. This is the I. Therefore, I is equal to Im. At t is equal to 0. The current Im, I is equal to Im is equal to V by R. That is maximum current, maximum charging current, at t is equal to 0. At any value of t, this is the source voltage. The switch is closed here. The switch S is closed. This is the resistance R. This is the capacitor C. The instantaneous value of that voltage is Vc of t. The current flow through the circuit is I at any value of t. Therefore, apply KVL. V is equal to IR plus Vc of t. V minus Vc of t is equal to IR. Therefore, I is equal to V minus Vc of t is equal to IR. This is the second equation. This is the second equation. Substitute in this is the first equation. Substitute here in first equation V minus Vc of t is there. Substitute second in first equation. V minus Vc in from first equation, V minus Vc of t is equal to V into e power minus t by RC. V minus Vc of t is IR. That is IR. IR is equal to V into e power minus t by RC. Therefore, I instantaneous current flow through this capacitor. This is the instantaneous charging current of the capacitor. Instantaneous charging current of the capacitor. Charging current of the capacitor, that is I is equal to V by R into e power minus t by RC. Here at t is equal to 0, the switch is suddenly closes. The capacitor acts as short circuit. The current flow through the circuit is I is equal to Im. Im is equal to V by R. Therefore, this is V by R is Im into e power. I is equal to Im. I is equal to Im at t is equal to 0. Maximum current flow through the circuit. Therefore, I is equal to charging instantaneous charging current of the capacitor. I is equal to Im into e power minus t by RC. This is the another equation. Charging at t is equal to 0, time graph. This is the instantaneous charging current of the capacitor small I. At t is equal to 0, the current flow through the circuit is maximum. And as the t value increases, that means RC, 2 RC, 3 RC like that. That value exponentially decreases like that. The charging current of the capacitor exponentially decreases. These are the two important equations. Charging analysis, we considered Vc of t is equal to V into 1 minus e power minus t by Rc. This is one equation. Charging instantaneous voltage across the capacitor is Vc of t. Instantaneous current I of t is equal to Im into e power minus t by Rc. These are the two very important equations which are very useful in gate analysis, network analysis concepts related to charging concept of the capacitor.